Okay, welcome back to another video. It's been quite a long time since I've actually uploaded anything at all, but it's time that I should start doing some more videos again. In particular, this video is going to be involving the chain rule, which is a really important formula and rule used in calculus. I'm just going to go through a couple of examples with it, but hopefully explain a little bit more about what it actually means when we find the derivative of a particular function. But anyway, the first problem I've got drawn here is x plus 3 cubed. And the graph I've got drawn over here is what this cubic graph actually looks like. And remember, the whole point in calculus is that you're trying to find, or you want to know, what the rate of change actually is. And the situation with any type of graph that's curved is that the gradient, constantly changes all the time. So you don't actually know, without finding the derivative, what the rate of change is. Of course, you can find it at any particular point by drawing a tangent line, but we want to know a little bit better. We want to know a little bit more detail. But with this problem here, which is this graph, x plus 3 cubed, if you expand it out, it ends up being x plus 3 times x plus 3 times x plus 3. And using the power rule and other derivative formulas, you can still find the derivative of this curve. But to do that, you'd have to expand it all out like this, and it's just, it will work eventually, but it will take a little while to do. There are better formulas to use to actually help us to cut corners a little bit. And in particular, that's exactly what the chain rule is. And I've got the chain rule drawn down here, and I've got it sort of mapped out a little bit on how to actually approach this same problem. So the actual formula for the chain rule is dy dx is equal to dy du times du dx. But what does that actually mean? Well, it's a convenient way for us to actually split apart this function and differentiate it into sort of two different sections. But what it means that we have to do is we actually have to do a substitution for this thing in the middle here. And the part of the function of this y function, x plus 3, we can actually rename that as u, okay? So we'll say in this function that u is equal to x plus 3. And effectively what that means is that we can rewrite the original function as y equals u cubed. So these are our sort of two functions here that we've sort of split up the original one. And this function is u in terms of x. This function is y in terms of u. And that's exactly what this chain rule formula is used for. We've got a dy du. So this will be dy du. And this is du dx, so this will be du dx. So we're effectively going to differentiate both of these formulas, or both of these functions, and then put them together. And that will give us the derivative of x plus 3 cubed. So let's just go ahead and do that. Dy du is going to be, so the original function, I'll write it here, x plus 3, wrong one. Dy du is this one, u cubed. And now we just need to find the derivative of y with respect to u. So remember, this 3 comes out the front, and it's 3u, and this 3, we subtract 1, so it's 3u squared. And that's the derivative of dy with respect to u. Okay, so that part's done. Now we need to do du dx. So du dx, this is the derivative of u with respect to x. So I'll write the original function first. And the derivative of this one, 3 is just a constant, so that's going to disappear. This is a power of 1 here, so 1 comes out the front. And then 1 minus 1 is 0, the x is gone. So the derivative of u with respect to x is equal to 1. So all we have to do now is follow what this formula actually says, and we're going to multiply these two parts. So dy du times du dx. So I'm going to write down dy du, and dy du is 3u squared multiplied by du dx, which is just 1. And we can simplify this by just writing 3u squared, which is, not too bad. But we have to remember that at the start, we did a substitution for this u value. And this u value, we let equal x plus 3. So we have to remember that u is equal to x plus 3. Therefore, we have to put that back in. So this is 3 times x plus 3 to the power of 2. And that is the derivative of y with respect to x. Solved like that. Now this is quite a straightforward example. X plus 3 cubed is quite a simple cubic function, but a lot of the time in derivatives and calculus, we actually get given functions that are a little bit more involved, like this. And for this one, we'll do exactly the same thing. We'll find the derivative of this function, and then after this, I'm going to use this as an example to talk about what the derivative really means, because I think this is a good question. So we'll find the derivative of this one using the chain rule and a u substitution like above there. So the first step with doing this, like so many questions in derivatives, is that we have to simplify this in a way that allows us to find the derivative fairly easily. So you can see that this is actually going to be similar to what we've just done. So I have effectively just sort of brought this to the top and changed this root sign to power of a half, brought it to the top, and it's become negative half. So this is what we're going to deal with. First thing is we have to label what is going to be u, what is y, all of this sort of stuff. So if we let u equal everything that's inside the brackets here, just like we did before with the x plus 3 example, we'll call u 2x squared minus 3x. Then therefore, y is going to be u to the power of negative half. And these are our two parts that we're going to differentiate. So let's go ahead and do that. dy du, this one here, we're just going to differentiate y with respect to x, with respect to u. And we just use the power rule like before. This is the power, negative half. So we bring that to the front. And that means that this is negative a half u to the power of negative half minus 1. Okay? Negative half minus 1 is negative 3 over 2. So that's going to be our new power, negative 3 over 2. And that's about all we can really do for the moment. Okay, so we'll move across to u now. And to find the derivative of this one, 2 times 2 is 4x. 2 minus 1 is just 1. The derivative of minus 3x is minus 3. So there we go. Now these two parts we are of course going to put together in the chain rule formula. So we'll take dy du, which is minus a half u minus 3 over 2, and all of this is multiplied by du dx, which is 4x minus 3. And at this point, all we're really wanting to do is simplify everything a little bit more. okay? And the next step we can do here, I'll just write it around slightly the other way. We can write 4x minus 3 multiplied by minus 1 over 2 u to the power of 3 over 2. So what we've done is we've sort of simplified this one a little bit. We've brought this minus 3 over 2 to the bottom, so it's a power of 3 over 2. The next step here would be we've got a power that is a fraction. That's not good to leave it like that. So let's change this to a root, a root value. 4x minus 3 is just going to stay completely the same. No changes there. So this one becomes minus 1 over 2. Now that the power 3 over 2 is going to be a square root of u cubed. So you can see that most of the time in derivatives, you're actually spending a lot of time rearranging and sort of simplifying formulas a little bit, because we want to try and get it into its sort of simplest and nicest form. So the next step here is going to be 4x minus 3 times negative 1 here. So that's just going to give us a minus 4x minus 3, and all of that is going to be over what is already on the bottom there, 2u cubed and square root of all of that. We're not quite finished yet because we have this negative and negative up the top. So let's simplify that a little bit. So we'll bring this negative in here and write it in the preferred way. So this would be positive 3 minus 4x. And the bottom is still going to be the same. 2u cubed, square root there. But of course, I hope nobody's forgotten that u is actually not a part of the original equation. There is no u. We changed it to say that u was equal to this 2x squared minus 3x. And therefore, we can finally put this u back into this function. And what we're going to be left with is the derivative here. So it was 2, and u was equal to 2x squared minus 3x square root, done. Let's write dy dx here. So the result here, actually, I forgot a cubed because there's a cubed here. So this is going to be cubed underneath there. And that looks all good now. So what we've got here is quite a sort of a big function here, and it's telling us that the original graph or the original function that we started with, which was this one here, if we differentiate it, we get a result of this function, and this function tells us what the gradient is at any point of x of the original function. Now, when I put that in words, that might sound a little bit confusing to follow. So what I've got here is something that is hopefully a little easier to understand. I've graphed quite a few things here. I've graphed the derivative. That was the derivative one. Okay. I've graphed the original function, and I've also graphed the tangent line at a certain point. But anyway, what I've got here, this blue graph here, which is now a little bit green, this blue graph here is the original function. The red graph is the graph of the derivative. So the graph of the derivative means that this is the graph of the gradient of the blue graph at every point of x. So effectively, if I choose a value of of 2, okay, if I read what the y value is of this gradient function, I get a result of negative 0.884. So that means when x is equal to 2, I get a solution of negative 0.884. And remember that this red graph is showing us what the gradient is. It's the solutions. It's the values of the gradients for all the points of x. So that means that the solution it gives me is the gradient of the original graph. So what it means, again, is that this blue graph here, which is now a little bit green, sorry, has a gradient at the point of 2. Its gradient is negative 0.884. And this is telling me, effectively, it's telling me the instantaneous rate of change when x is equal to 2. And that's what this the derivative is useful for. I can use this function to tell me the gradient or the rate of change at any point of x. So for example, I could take x is equal to 4. And whatever the solution is when x is equal to 4, I'm not sure exactly what that is, but you can see that it's quite close to 0. It means that the gradient of the original function will be quite close to 0. And you can see that this gradient here, it's fairly flat. It's not 0, but it's approaching 0. It's definitely approaching 0 because there's actually an asymptote there too. But this is the usefulness of finding the derivative of any particular function. It will tell you the gradient at any point of x for the original function that you differentiated. Okay, so I'll just get out of this one. And that's really all I wanted to show in this video here. I just wanted to do one example or two examples and just sort of show on a graph what this means a little bit. But anyway, I hope it was useful and thank you very much for watching.